Hi, welcome to another installment of the Linearity 2 videos. You're joined today by Mark Somerville and my esteemed colleague John Geddes.
Hello.
And we're going to be talking in this series of videos about modeling what we think is sort of one of the simplest possible distributed systems. And our objective in doing this model is not really that you're going to spend a lot of time modeling this particular system, although we'll certainly do some things in class to get at it, but more that by looking at a simple system, it's possible to see what some of the really key ideas are in modeling distributed systems. So the kind of system we're going to look at is one that will look somewhat familiar to you from back in the days of ModSim. So we're going to think about the case of, say, some bar of metal, right? So this is like, let's say, an iron bar. And what we're interested in is understanding how the temperature in the bar changes over time. So hypothetically, let's say we've got this bar, it's outside, it's been outside for a while, we're outside, and we decide to take one end of the bar and stick it in a very hot fire, right? So there's a high temperature on this left-hand side, right? And then the rest of the bar and the right-hand side, start out being at T right, which is the outside temperature. And what we're interested in doing is understanding how does the temperature in this bar change over time, what's actually going to happen. And if you think about this, this is a really good example of this kind of distributed system because qualitatively speaking, you'd imagine that at each point along this bar, the temperature is going to have a different value, and that temperature is going to have a different value at different times, right? So this, in this case, what it would mean to actually find a solution to this problem would be to ask the question, to be able to answer the question, what's the temperature along the bar as a function of position and also as a function of time, right? So that's what we'd like to get to. We're not going to get there first, though, John. I'm sorry. Hope you're okay with that.
I'm okay with that, Mark.
All right. What we're going to do instead is start really simply and try to abstract this to the simplest possible model. And I'll propose for the simplest possible model that we harken back to the days of ModSim and we do a stock and flow model for this.
Great.
Okay. So I know it's been a little while since you've done ModSim, so tell me when I say things that don't make sense.
Okay.
So what we're interested in doing is thinking about this bar, and I'm going to think about this bar basically as being a single sort of thermal mass, right? So I'm going to make sort of a point mass approximation where I kind of take the whole bar and stick all of its thermal mass at one sort of point in the center of the bar. And so I'm going to collect this whole bar down to be a single sort of thermal mass. So the bar is going to have one temperature. And I'll call that T sub B for temperature of the bar. And
it's going to have a volume associated with that mass?
Well, I'm going to think about that as being a point mass. So I've basically taken all of that, all of the sort of matter in the bar and kind of put it in one spot and said it has one temperature.
Got it.
And then obviously the bar is connected to the rest of the world in a couple of ways. One of the ways the bar is connected to the rest of the world is connected to this T left. So there's some kind of connection between this bar and the rest of the world. So I'm just going to draw a sort of resistor symbol to represent that connection. And we can figure out what that connection is in a second to T left, right? And also some kind of connection to the rest of the world through the bar to T right. Right?
And Mark, why do you draw a resistor?
Well, I draw a resistor.
Because I seem to remember from things like ModCon and iSim and all the various versions that you could have resistors and capacitors and inductors. Why do you draw a resistor?
I think it's because my background is electrical engineering, John. But it's also because we often talk about thermal resistance. And in the same way that a sort of electrical resistor resists current, that is when you apply a certain voltage across it, there's a certain amount of current that flows. Objects also have a thermal resistance. When you put a certain temperature difference across it, a certain amount of heat energy flows through the bar.
Perfect.
Okay? So, and a lot of the ideas end up being very similar. So if we think about this, and another way of thinking about this same thing is actually to draw a stock and flow diagram for this, right? Because we basically have two ways that energy can get into the bar. One way that energy can get into the bar is here from the left, and the other way energy could get into or leave the bar is to go out on the right. So a sort of stock and flow diagram for this might look something like this, where the stock I would be keeping track of is what the energy in the bar is, right? And the energy bar in the bar will change over time. It will change over time in a way that depends on what the sort of T left is. It will depend on what the current energy of the bar is, and it will also depend on what T right is. So
Mark,
that's another way of representing this idea purely qualitatively.
And can I ask you, in this bar, I mean, you're suggesting that the only way for energy to get transferred is through this face or that face, but presumably there's this whole surface of the bar.
Absolutely right, John.
Are we just ignoring that?
We are totally ignoring that.
Okay.
And that's really a terrible approximation for us to make, unless what we're doing is sort of taking this right-hand side of the bar and maybe we're putting the right-hand side of the bar in ice water or something, so that that's in very close thermal contact with the ice water. The left-hand side is in very close thermal contact with its hot thing. And maybe we put styrofoam around the outside of the bar, right? We're making all kinds of abstractions in dealing with this.
But we're certainly, however we think about that, we're certainly ignoring any of the temperature variation this way, or presumably this is like a circular cross-section maybe.
Yeah, I mean,
we're just ignoring all that.
In the real world, right, this would be a sort of three-dimensional object. And so we would actually have to think about what the temperature was as a function of position inside that object, where that position would be a vector in 3 space. And presumably you'd have all kinds of interesting stuff happening at the surface. You'd have convection at the surface. The top of the bar would probably be a different temperature than the same position at the bottom of the bar. So it would be a much more complex problem. So I'm really thinking about this as a bar that's insulated on the sides, where only the two ends are being held at a temperature, and I'm interested in how the temperature in the bar changes.
Got it.
It's kind of a dumb problem. I'll acknowledge that. Okay, so given that sort of very simplified system that we're dealing with, there are two ways energy can get in and out. And so from this stock and flow, we would then say, okay, well, how do I sort of predict the behavior over time? Well, I can translate a stock and flow into a differential equation, because it's pretty clearly a continuous time type of system, right? So I'd say the time rate of change of the energy in the bar is going to somehow depend on what's happening here and depend on what's happening here. So let's deal with this first. And there are a number of things that this depends on. One thing that this is going to depend on was what the difference is between the outside temperature, the left-hand temperature, and the bar's temperature, right? If the two things are at the same temperature, there's not going to be any energy flow. If the left side is hotter than the bar, there's going to be positive energy flow in, and so on. And certainly for most systems, we use Newton's law of cooling, which tells us that energy flow is proportional to that temperature difference. So I should get some proportionality of the left-hand temperature minus the bar temperature. Then I need to ask the question, what's the nature of that proportionality? Well, if I go back to the bar and I think about the bar, if I draw the bar as like a cylinder, right? So here's my bar, and then here's my sort of center of the bar, that's my thermal mass. Well, the bar has some cross-sectional area, right? And if you think about it, as I make that bar bigger, it's going to be like making a hose bigger. And as I increase the cross-sectional area, its resistance to the flow of energy will be lower. In other words, more energy will flow, right? So the amount of energy flow should be linearly proportional to the area. If the bar is some length L, right? Well, the distance that I actually need to travel from the left-hand side to the center of the bar is going to be L over 2, and just like when I make a hose longer, it's harder to push water through it, the resistance will increase as I make this longer. So I'm going to divide by L over 2 to represent the fact that the sort of the thermal conductance of this is going to drop as L gets bigger. Finally, the bar is made of something. It's made, we said, of iron, and iron has a thermal conductivity, which is represented with the symbol kappa. It has units of watts per meter Kelvin. This is a physical property, and the higher the thermal conductivity, the more watts are transmitted per meter Kelvin, so that goes there.
And so, Mark, just so it's clear to me, because I often have to do this for myself, if I just think about units here, and just make a little notation. So temperature we measure in Kelvin, right? And you just said area we're going to measure in meters squared. Kappa, you said, is watts per meter Kelvin. Length is presumably in meter, and so the right-hand side boils down to watts.
Exactly
And a
right.
watt, if I'm not mistaken, I was a physics major, is joules per second.
Yep.
So we've at least got the units right.
We do seem to have the units right.
Yeah. I actually had another question about this because this is actually a particular model for heat transfer.
This is absolutely
right?
a model.
This is heat transfer for what?
This is heat transfer due to conduction.
Conduction.
Right. So the idea is that you don't actually have mass that's moving around. It's instead the fact that individual molecules are vibrating and making the molecule next to them vibrate, and so on.
So convection, which we've met, would be something different. Radiation.
Right. I mean, typically convection models, in the simplest version of convection models, look very similar because you simply use a heat transfer coefficient instead of this sort of more physically based factor out front. So convection often is modeled just with a temperature difference. But certainly the physical nature of it is different and also much more complicated than conduction. Okay, so this term represents this flow. Once we've thought through that term, it's pretty easy to see what the term should be on the right-hand side. So we're going to be losing energy out of the right-hand side, assuming that T right is lower than the temperature of the bar. So I'm going to have minus kappa times A divided by L over 2 times T bar minus TL, right? And at this point, I could start to collect some terms and see that I've got a TL here, and I've obviously got something wrong here because I've got a TL there, which should be T right, right? But I've got two T bars running around, both of them have the same sign, so I could start to collect some terms. But maybe we should pay some attention to this right-hand side, right? Because the left-hand side is all in terms of temperature. The right-hand side has to do with what the energy of the bar is. So we need now to actually translate this energy into temperature, translate temperature into energy. So the question we want to ask now is, how does U bar depend on temperature?
And that's something that, if I'm not mistaken, you folks would have seen or thought about in Mod Sim a long time ago.
A long time ago, they did probably see that and
too.
think about that. Certainly, if they've taken thermo, they've thought about it much more than either you or I have. But the sort of idea that we're going to exploit is this idea that, in general, there's a heat capacity associated with materials, which has to do with per degree Kelvin, how much energy does it take to raise the object 1 degree Kelvin. So the sort of model that we'll use is U bar is equal to some specific heat times the density of the material times the volume of the material times what the temperature of the bar is. Okay? So specific heat is joules per Kelvin per volume per kilogram per volume, or joules per kilogram per Kelvin. Right? So then it's the amount of energy it takes to raise 1 kilogram, 1 Kelvin. And I know what V is here because this energy of the bar has to do with what the temperature of the bar is, and we're modeling the temperature of the whole bar. So this V is simply A times L, right?
Correct.
Okay, so now I could come back over here to this right-hand side and actually write this out as a differential equation for energy. So I get T...
Or the temperature in the bar?
Or temperature in the bar. Let's do temperature in the bar, which is what I meant to say. So dt bar by dt is equal to, and now I need to do a lot of sort of multiplying through and dividing through, and I'm going to make a stupid mistake here, so save me when I do. But I think that I'm going to end up getting 2 times kappa divided by C times rho times L squared times the quantity T left minus 2 T bar plus T right.
You did that perfectly, Mark.
I did.
And it's probably just worth reminding everybody that he's just collected some terms, substituted in the energy in here, and done a little rearrangement.
Yep. Okay.
Perfect.
So great, we've got a differential equation Differential equations should sort of remind you of classes you've had before. Both linearity and ModSim have dealt with these. Obviously, in ModSim, we dealt with how do we solve this differential equation using numerical approaches, using ODE45. And in linearity, you dealt with some of the sort of analytical behavior of this. So we could now take some time to look at this differential equation and think about how it's going to behave, and also think about what this model would tell us and not tell us about the physical system.
And maybe we should leave that for another video.
I think that's an excellent idea, John.